Okay, hello everybody. Today's class we are going to tackle an interesting topic about graphics, something that is going to go tied together to what we did last week, which was illumination. So today's topic is shadows and how we can achieve more realism in rendering using shadow maps, and it's a technique that has been for many years. Um, Shadows is a complex process in the sense that we have solutions to tackle that from the GPU, but none of them are perfect. They all have different minor problems, and to have some basic shadow maps, it's not super complicated. You will see today, although it requires a little bit of playing around with the GPU in smarter ways. But when you want to go to very beautiful, perfect shadows, that's when things get very complicated. So anyway, let's go to the slides where you will see there's a lot of material about shadow maps. I put a lot of links, references, everything, and I had tried to clean up most of the complexities of shadow maps, so you don't have to worry too much. But it still, well, takes time to get used to using shadow maps and to get the perfect shadows for your renders. Okay, so without further ado, let's go to the slides which are here. Okay, 1 second. Yeah. Okay. So real-time shadows, as we see, is a continuation of the previous class. Okay. So what we want to achieve, it's something that looks like this. So we have, this is a classical scene on 3D, and you can see that it doesn't look very well. You can see this chair here, it seems like it's not touching the ground, but as soon as you put shadows, boom, it grounds the object to the floor. Also here you can see how it doesn't look realistic. We have always this strange impression that this is not, like there's something missing here, and when you put the shadows, it all grounds perfectly. Okay, so let's see. Blender has an option to control shadows. You can see here, if you at any moment you want to play around with enable and disable shadows. Let me show you so you can see it. So here I have this scene with this car, and as you can see, there is no shadows. But if I just go here and enable the shadows, I can see it. Okay, and it has some parameters that you can play with. So more afterwards, when you have more clear about how it works, I would recommend you to try to check playing with the parameters to see what happens. Okay, it's important to realize that Blender is using shadow maps. Okay, the same technique I'm going to explain to you is used by Blender here. When you use the render, call it Eve, the real-time renderer. If you use cycles, it's going to use a different approach, which is ray tracing, and in that case, the shadows are slightly different, has better quality. And the reason why I say this is because it's good to see that some of the problems you're going to face during this assignment are, well, there are problems that happens to everybody when you do shadow maps. So the shadow maps are not perfect. Okay, so as I said, why we need shadows is for many reasons. Like if I show you this image on top here, and I tell you which one of these cubes is bigger, which one of these cubes is touching the ground, or which one of these cubes is in front or the others, it's hard to know. I mean, you can have some guess, like this one looks bigger than this one, so maybe this one is bigger, but depends a lot on different situations. It's when you have the shadows that you understand better the depth of this scene. So you can understand this one is floating, this one is biggest touching the ground, etc. Okay, so that's why shadows are super important, not because only for quality, but because it grounds objects. It tells you where is everything, and if you don't have shadows, it's easy to get lost a little bit on a scene. There's another common problem when you don't have shadows, because maybe you don't care so much about grounding objects, because the textures already help you ground objects usually, is because it can happen that you have a light behind a wall, like here. There's lights behind this wall, and because there's light behind this wall, when we compute the illumination, in this case the specular reflections, those speculars can be seen through the wall, which doesn't make any sense because the light should be blocked by this wall. So this, for me, is the worst case, or the reason why we really need shadows. When you don't have shadow maps, or shadows, sorry, you start seeing this kind of shiny objects on different places that doesn't make any sense, and breaks, for me, it breaks totally the immersion, mostly when you're in interiors. So if we can apply some sort of shadow map, these lights won't be able to cross, and then you won't be able to see them here. Okay, and this is a classical example I always show. This is the mesh of Lee. You already probably know because you have used it in different courses. And here it looks kind of bland. I mean, I don't know, it's not looks very interesting for me. It doesn't look very dramatic. But as soon as you turn on shadows, I don't know, it starts feeling more interesting. Like it has some more dramatism. If I move the shadows, the light, you can see how the position of the lights creates these beautiful shadows on the face. And even if I try to go more exaggerated about the angle, you can see how this is very dramatic, like it's mysterious or something like. So compare this that looks very like mysterious face with something without shadows, which looks very dull. Okay, and the same if I put the shadow, I don't know, below or something like that. Okay, so as I said, shadows are super important, and we spend a lot of time when we render 3D scenes tackling the concept of shadows to improve them and to support as many shadows as possible, because they have a cost. We will see later. So we want to have a system that allows us to have shadows and as cheap as possible, because we want to be able to put shadows on our scene as much as we want to. Okay. Besides having shadows, it would be nice that the shadows has all the properties that we are used to see. Like for instance, penumbra. Penumbra is this beautiful blur shadow that when the farther it is the shadow from the casting object, in this case the casting object is this one. This is the one that is producing the shadows here. If the closer to the point is closer to the casting shadow, then it should be sharper. But the farther it is, it should be blurrier. Okay. This is called penumbra. We won't be able to code this feature on the engine because we don't have much time to code this, and this is a little bit complex, but it would be nice to have this kind of effect. Okay, and so let's go back again to the problem, and we're going to tackle the concept of what we really want to do, or what we really want to know is, given a point on a 3D scene while we are rendering, we have these points here. If we have a point in our 3D space, we want to be able to somehow know if this point was behind another object. Between the light and at this point there was an object, or between the light and this point there was no object. Okay, this is the question. Can we know if this point is behind something or not from the point of view of the light? And if that's the case, then we have this shadow factor that we multiply by the amount of light. So if it's here, the shadow factor will be 0, while if it's here, the shadow factor will be 1. Okay, so that's it. The problem is that obviously GPUs don't have a function to say, hey, there is an object between here and here. If we were using a ray tracer, remember that ray tracers contain a description of the whole scene before you start rendering. Because they contain a description of the whole scene, that's nice, because that means that in any moment I can say, hey, there is a triangle between this point and the light, and ray tracers can solve that problem very easily. Well, very easily. It's supposed to be faster if you use GPU, but still, conceptually, it's easy for them because you only have to test this ray against all the triangles to tell you if there's something in front of it. Okay, so if you are doing ray tracer, if you are using a ray tracer, shadows are the cheapest thing that you can have. Okay, from the point of view complexity of coding, not from the point of view of computational, because they are still taking a lot of time. But when we use raster, remember how raster works. We are rendering every triangle one by one, and the GPU doesn't know which triangles are going to be rendered in the future. It can know what have been rendered before. I mean, we have the frame buffer and the depth buffer, but it doesn't know what is going to come next. And because it doesn't know what's going to come next, it's impossible for the GPU to know there's going to be a triangle between this point and this point in the future. They cannot predict the future. So raster is not a good solution when you want to use shadows, unless you try to rearrange this problem to use the GPU in a smarter way. Okay, so some engines from the very beginning, when they wanted to have shadows, the only approach they could do was, hey, we are going to pre-compute these shadows using ray tracing. We're going to store these shadows in a shadow cache, which is this kind of texture, and using this shadow cache. Using this shadow cache, then I have only to read the texture from the GPU to know how much light do I have to put in any place. Okay, this is still being used by many engines because it's a cheap solution, but obviously this has a horrible problem, which is that first, that objects cannot move, and the light and the shadows are, well, as sharp as the light map. And because the light map has to cover the whole scene, we have to have a whole texture for every single pixel on a scene. At the end, they have low resolution, so you can see obviously this kind of pixelated things on the surfaces. So baked shadow maps or light maps, sorry, it's common. You can see it in many games, but only on some specific games that don't require many objects to be moving. And for instance, in this kind of games, if the characters have to be walking around, they won't have shadows because they are obviously dynamic. So you see this mostly in mobile phone games because well they usually have lower GPUs, although recently they have better ones. Okay, and to generate this this light map, sorry, and with all the illumination and everything put inside and with the shadows and everything, you can use a ray tracer. You don't have to care about performance because you can generate them, like it can take several hours to generate, and when you have it, you just have to put it inside your 3D scene. Okay, you can use ray tracing if you want to generate these light maps. It's quite common, and there's many solutions. You can even generate them from Blender if you want to, and export them as a regular texture that you can use inside your engine. Okay. But if we want to have something that is more real time, because it's always more interesting to have something in real time, the first approaches to shadows I saw, they use this trick. This is a very simple trick that you can use now, which is if I have an object and I want to have a shadow below the object, the simplest trick is I render this object this teacup. I render it again. First for the regular teacup, but I render it again, and the second time I render it, I flatten the object. Check here. I'm saying that the wall position of every vertex, I do this in the vertex shader. I say that it's one constant value. What I will do that is would squish the object and make it flat on the floor. And if I render this object as a black thing, then boom, I have a black shadow below. It gives some grounding, like now I have a black shape below. I can control even if I wanted the angle of the light using this kind of projection of if I have a wall position of the light. There's tricks to make it not right below, but in of an angle if I wanted to. But still, obviously, this is not perfect, mostly because you can see that this object doesn't cast shadows on himself. You can see there's no shadows here, although it should be shadows. And also they don't cast shadows on other objects. And also this only works if the floor is flat. If the floor was different steps or something, this doesn't work. So a cheap approach that some people used many, many years ago. The first true shadows that we saw in a video game was for Doom 3. In the 2000, they were using this approach called stencil shadows or shadow volumes, which is kind of not complex but CPU intensive, because the idea is that you have to you have to walk through all the triangles in the scene and find the edges of the triangles where one side of the edge is in the shadow and one side of the edge is not in the shadow. And when you have that, then you extrude that edge in the direction of the light is here, you extrude it in the other direction. And you construct this kind of geometry on real time. Every frame you have to construct this yellow geometry. And then using the stencil buffer, you can make a trick where you render this geometry and then you disable the stencil buffer, something like that. And you get these beautiful, super sharp shadows. Okay, they are very, very, very sharp. So I think we will see later when we use shadow maps, the other technique that we're going to code is that the shadows are a little bit blurry, but with these ones you get super sharp shadows. Still, they have some problems. They require a lot of rasterization time because you have to rasterize a lot of triangles and you have to compute this projection. And well, it's a little bit complicated to use and to code. So besides this game and a couple of more games, this hasn't catch up. There are not many games using this approach, the stencil shadows. Although I was reading an article 2 days ago where they were saying it would be nice that some more games try to use this kind of approach. Okay, another solution, which is not perfect, but it can work, is maybe you don't want shadows per se, but you want these beautiful effects on the floors, like there's some sort of light projected on this space. And for this one, you don't need to have any kind of shadow map or technique. You can achieve this kind of effects. Here I have an example. If I have this light, this spotlight, I can go to the spotlight. Let me go here, and I can have a texture and project that texture on the surface. If I go here and I take this texture here, you can see how it's projecting, and it looks like there's some sort of shadow here. Although it's not a shadow, it's just that for every pixel that we are rendering, we are going to that texture and applying that texture here based on the view projection of the light. Um, the problem with this approach is that we have a regular object like this cube here. From here it may look like there's shadows, but if you look at from here you can see there's no shadows. Okay, so this is called projective lights or light cookies. When you have a light that have a texture that is being applied, here I use this that has more black and white stuff, but you can use any texture. Like if I use this texture, for instance, you are projecting this, and you can see if I now move this light, for instance, let me select this light so I can move it. So if I move this light, you can see how the texture moves. Okay. By the way, this is always nice to have, because instead of using this crazy texture, you use something more like, let me show you. Do I have light cookie like this one? You can give the effect that this light has this nice pattern of regular lights. When some people has to construct, architects and designers, they use this kind of patterns to know which kind of lights they want to use, because these shapes depends on the shape of the lights inside the light bulb. There's like a email list about this. Well, there's some slide at the end about this. Okay, so sorry. Okay, so this is this is not shadows, but still we can fake a little bit the shadows. Okay, but let's go to the problem that we are trying to face today and see if we can have a way to solve it in a more interesting approach. Okay, so the idea here is, given a point on the 3D wall, we want to have a way to query the from the shader, okay, because we are illuminating from the fragment shader. We need a way to know if in between this point and this point, the light, is there any geometry in the middle? If there is geometry, we don't apply the illumination. If there is no geometry, we apply it, and if there is geometry, we don't apply it. Okay, but for that we need some sort of distance cache. Okay, some sort of way to the GPU to know what objects are on the scene, at least for this area, the area of the light, where the light is affecting. Pre-compute somehow which points are visible by the light and which points are not visible. If I say it like this, you probably think Javi hasn't explained anything about that, so it's impossible because we don't know how to do that with the GPU. But you already know the how to do this. The problem is that you never bended this problem to feed it to the GPU. So let's discuss again the problem from a different point of view. We know that from the shaders, from the fragment shader, there's only two data that we can read. We can read the uniforms and the textures. Okay, so, and uniforms are usually very limited, so it's not like I can pack a lot of information in a uniform, because the amount of memory that uniforms can have is small. In modern APIs, by the way, you can have like unlimited, like access to all the memory of the GPU, but with the cost of obviously having cache misses and all those things. So performance-wise, it's like you have a lot of problems, but you can. But currently, let's assume that we are using an old version as we are now. So the only way to access a lot of data is through textures. That's if we want to read a lot of information, we go always to textures. So we need some like stored in a texture how far away is every pixel from the light. And obviously, if we have to rethink and rethink, how can we store distances on a texture? Well, we do it constantly, the depth buffer. Remember that the depth buffer that we are using currently for the occlusions, it's already a cache that contains for every pixel how far it is. So it contains distances. And for our algorithm to do shadow maps for one light, makes sense, because what we need is the closer point to the light. We don't care. I mean, we want to know if between 2 points there is something in the middle. We don't care if it's the closer, the farther, just to know if there's something in the middle. So we can have this if we have a depth map from the point of view of the light. So how the algorithm works. Shadow mapping, this is the name that we usually use. The idea was created during the 70s, although in the 70s they didn't have the power to execute it in real time. It had to wait 20 years. The idea is that we are going to First, before we start rendering our 3D scene, like our illumination pass, we're going to put a camera in the position of the light, okay, facing on the direction of the light. And this camera is going to render the whole scene to know what's visible. But it's not going to store the color, because this camera doesn't want to know the color of every pixel. Only wants to know the distance, okay? So we are going to put the camera here, pointing at the 3D scene, and we are going to do a full render. From that full render, we will store the depth buffer. You will have something like this, okay? Once we have this depth buffer, we keep it in memory, and then we can go to the next steps, which is when we render the illumination pass for every pixel of the scene, we can say, hey, I know the distance of this pixel to the camera, I can know it very easily. But what's the distance of this pixel with the light? And if I project this pixel on the light, in which position of this texture will fit? For instance, if it's the nose, then it will be this coordinate here. Then if I know exactly any 3D point on the wall where will fit inside this shadow map, I can read the depth from this texture, I can compute the depth from the pixel to the light and compare them. If the depth is the same, then it means that this object was visible by the light. But if the depth on this texture is smaller, it means that there was something in front of me between the light and this point. So that means that this point shouldn't have light. And then if that's the case, I don't render the light. I multiply the light by 0 or don't compute the light at all, okay? So very cheap in the sense that we are only doing a fetch on one texture. The only expensive part is I have to construct the whole shadow map. I construct the whole shadow map implies that for every light that has shadows, I have to render the whole scene, okay, from the point of view of the light. And if I have like 3 lights, that means 3 renders of the scene plus the final render with the illumination pass. Okay, so that's why shadow maps tends to be, well, could be very expensive. I will tell you some tricks afterwards, so how can we mitigate a little bit the performance problem, okay? But that's the idea. First, we render the whole scene from the point of view of the light. We store it in a shadow map, on a depth map that we call the shadow map. And then when we render the illumination pass, then we use this texture here, okay? So you can see that now our render pipeline has moved from, like before, we just rendered the whole scene, and now we are in a new point where we have to have 2 steps. First, we render shadow maps, and then we render the scene, okay? So you can see how our pipeline is getting more complicated as we add more steps on this process, okay? When we store the shadow map, the depth map of the point of view of the light, we can use the depth texture if we want. You can pass the depth texture to the shader. It's possible. There's no big problem. But if you pass the depth texture to the shadow, to the final pass, depth texture usually have 24 bits per pixel, which is a lot to store depths. But if you want a little more, you can always try. There's many tricks. One of the tricks could be that you can store in the RGBA. This is 4 components of 8 bits, so it's 32 bits. You can decompose the distance between these 4 elements and store them different. So here you will have some image that look like this. It's kind of strange colors because you're storing distance as colors. Or you can just use the depth map, as you can see here. So you can just store the depth of every pixel using the depth map. Currently, you don't have to do anything. While for this, you have to encode in the color. For this, you get it for free because you just render the scene and then you get the depth buffer and you use it for something else, okay? Because we are going to render not to the screen, but to a texture. Remember that we will have to use the FBOs, the thing that we discussed the other day when we were talking about what GPUs can do, okay? So here's a code, by the way. If you want to pack the distance, like here's the distance, into an RGBA color, assuming that the distance goes from 0 to 1, this is a code, okay? It multiplies many times by 256 and do some hacks here, and at the end you get this vector 4 that contains the distance encoded, okay? If you encode the distance in a color, probably when you are rendering the final illumination path, you will want to reconstruct again the distance based on that color. So you can do it here. This is the opposite function. So this codes distances to color, and this unpacks colors to distances back again, okay? just if you want to use colors. But we are going to use the colors. We're going to use the depth buffer because it's the simplest one. This makes sense if you want maybe to have bigger maps with a lot of objects in the distance where you want to have more precision for the depth, but for now we don't care. Okay, problems of shadow maps that we have to be very, very aware. First of all, shadow maps don't have an infinite resolution. We will have to set up how much resolution we want the shadow map to have. When we do that rendering from the point of view of the light, we have to specify if we want, I don't know, a texture of 1024 by 1024 or bigger. And that has an effect because every texel, okay, you can see this area, yellow area, as the shadow map that we render. Every texel at the end will represent an area of our 3D world, okay? And because it's an area of our 3D world, you can see here that every texel of the shadow map, every pixel of that texture has a width on the wall. The less pixels we have on the shadow map, if the shadow map is very small, that means that this distance between will be bigger, so we won't be able to compute different shadows inside those pixels, different details, and this traduces at the end to very bad quality shadow maps. You will see like huge pixels on the shadows. And well, for that we really want to adjust well the size of the shadow map, not only the size of the pixels, also the size of the whole area inside the shadow map. Okay, so as I said, shadow maps are not perfect. They don't give you crisp shadows, and they are more pixelated, and we will have to tackle that. Also, when we are going to put a camera and render the shadow map, not all the things in the wall are going to fit inside that shadow map. We're going to put a camera, we're going to specify some properties about the frustum. In this case, for instance, because this is a directional light, the frustum will be orthographic, it will be more like a box. While if it was a spotlight, it will be more like a frustum, like a pyramid, like a cone. By the way, for point lights, I'm not going to say much now. Like for everything I'm going to explain now about shadows is only for directionals and for spots because they are easy to render. You just put the camera pointing in the direction of the light and you do the render. For point lights, because the point lights emit light in all directions, you can put a camera here that renders the whole scene in all directions. So there are hacks, but we will talk about that later. Okay, but for now, keep in mind that for any kind of directional light, you just put you create a camera and you set it up like the eye of the camera is in the light position, and the target, the center of the camera, is in the light position plus the light direction. Okay, so it's going to point in this direction. Okay, and then you have set a camera ready to be used. Okay, if we were using a spotlight, we would use a set perspective because it will be perspective. And if we were using a directional light, it will be set orthographic. Okay, and then we render the whole scene. And when we have rendered the whole scene, I will have an example later. We need to have a function to know if one pixel is in front or behind an object. So while we are doing the rendering of the 3D scene, for any given point, we need to know the pixel value of the distance on this and on the light, on the shadow map. Okay, how we do that? Remember that when you render a 3D scene, you're multiplying every vertex by the view projection matrix to know the 2D coordinate. So if we want to know one given 3D world point during the final pass, the illumination pass, where does it fit? What we do is multiply it by the view projection of the light, not the camera, because that's already done to render the triangle. But for every pixel that we want to know if this is in shadow, we multiply the 3D coordinate by the view projection that we use to generate that shadow map. And that will give us first the pixel position inside the shadow map, like at this point here, where does it fit in this cone? It would go and project it and say it will be this pixel here in the image. From there, we can convert it to UV coordinates and read that texel exactly from the shadow map. And then we know the distance from the light to this point. At the same time, we also know the perfect distance if there was nothing here, because when you multiply it, you get the distance also. So if we compare the distance from here to the distance we get from the texture shadow map, we know if there's something in front of it. Don't worry now because you will see it better when we have the code in front of us. Okay, so these are the steps. When you want to do the illumination pass and you want to know if there's shadows, for every pixel, first, you project the 3D position of that wall position that we want to know if there's in shadow or not by the shadow map view projection, okay? By that matrix that we have to pass, extra matrix that we have to pass to the shadow, sorry, to the shader that contains information about where it was rendering the shadow map, okay? The problem is that when you multiply by this view projection, you're going to get homogeneous coordinates. Don't worry about it. You have to divide by the W to go to clip space. Okay, this is a common thing that we did also on computer graphics when we were talking about projections. Remember that clip space goes from -1 to 1, but we want to render textures, and textures go from 0 to 1. So we compare from clip space to UV space, like we have a number that goes from -1 to 1, and it has to be from 0 to 1. So in those cases, you multiply by 0.5 and you add 0.5, okay? And that goes from -1 to 1 to 0 to 1, okay? And then we extract how far away is this point from the light, and then because this has to go from -1 to 1 and the shadow map goes from 0 to 1, we convert it from -1 to 1 to 0 to 1, okay? And now we have both distances, the distance from the shadow map and the distance from this point to the light, and then we compare them, okay? Well, we read the texture, sorry, and we get the other one, and then we compare them, and if one is smaller than the other, it's probably it was on the shadow, okay? A lot of mathematics here, but you will see that these mathematics are super cheap, so you don't have to worry too much. Okay, so here you can see a little bit more explain in general the problem, okay? Okay, but there's many problems when we use shadow maps. I said before that shadow maps are a topic where there's many things written about, many algorithms, and the main reason for that is because we don't have a perfect solution. If you don't have a perfect solution, well, I want to be aware of the problems we're going to face, okay? So, first, the performance problem, which is we have to render the whole scene for every light that has shadows. And that's why many games try to have lights that doesn't have shadows, because otherwise they are going to have a problem. And if the shadows is for point lights, that's super expensive, because the tricks to solve point light shadows imply usually rendering the scene 6 times, and we will see later. Then textures has a limited resolution. That means that you're going to see this problem a lot. I don't know if you can see it well, but there is these pixelated areas on the shadow maps because, well, there's a limited resolution. I mean, you're using a texture, and texture has a resolution. You can increase the resolution if you want to, but the more you increase the resolution, the more time it takes to render the shadow map, because it needs to raster more pixels. So increasing the shadow map is not always the best solution, and so you have to play very well with the resolutions. Another problem is, okay, we know that shadow maps have a limited area of the wall, but in the case of directional lights should be covering the whole wall. They should go from like very far away to very close. So I cannot have a shadow map that covers the whole map from point to point, because it will require, or the resolution is huge to cover the whole map, or the resolution will not be huge, but then every texture will cover so many meters that you won't have many shadows in small objects. So this doesn't work very well with directional lights. We will see how we can tackle that. Also, there's a problem that the buffers have a limited precision per component. That means that you can store more than 24 bits, and that can produce problems. We will see one of common problems. And also that this is a common problem, that when you have shadow maps, if you are generating the shadow map of a light that is very far away, and I'm using, I don't know, 1000 pixels shadow map for that light that is super far away, I'm wasting a lot of resources because I have to render a lot of information. And when I'm rendering, from my point of view, the final scene, maybe this is going to be like, I don't know, 20 by 20 pixels on my screen where that light will be visible. So it's a problem when you just throw light maps and at the scene, because if you don't handle well the shadow map size for every light, it could be, well, you're going to waste a lot of resources. Also, if one light is not visible by my main camera, doesn't make any sense that I compute the shadow map. Okay, so here are some tricks to when you generate the shadow maps, to make them a little bit faster. It's not incredible tricks, but at least the basic thing is, first, that we only update the shadow maps if the light is visible from the main camera. Okay, if my main view that I'm going to render the scene, if that light is outside of the view, and you can do that using frustum cooling, things like that, then don't generate the shadow map because you're wasting resources. You're generating a shadow map for a light that is never going to be visible. Okay. Then also, if we have the max distance of every light, we use that when we render the scene. So the frustum that we're going to set for the view when we're going to render the shadow map, if we know this light cannot go farther than, I don't know, 10 meters, we don't need to render objects that are 10 meters away from the camera. So we use the max distance of the light as the far plane of the camera. Then another trick that is harder to code, I can give you a good solution, is that if nothing moves inside the light vision, then the shadow map will be exactly the same from the previous frame, so you don't need to regenerate it. The problem is that to know what has changed inside an area of view is not easy. So for this one, if you wanted to try the trick like flags that you have to set up, but I won't recommend to do this one. Also, another trick would be that you don't need to re-update the shadow maps. Like if you render you can put all the shadow maps and you know that the scene hasn't changed, you can keep reusing the previous one. Many video games, for instance, what they do is that they generate all the shadow maps maybe on a startup when you enter a map, for instance, and then they don't, because they know that the map is not going to be changing because objects are static. They don't need to regenerate the shadow maps every frame. Maybe you only need to regenerate them when something moves. Because characters can move, maybe for characters they don't have shadows, and that solves the problem. Or there's another trick where they store the shadow map of the static objects, and then they generate a new shadow map of only the character. So you have one that never changes, which is the static one, static objects, and then when you need to re-update it, you copy the static one on the view now, and then you start from there. So you can render all the static objects instantly because you already have pre-computed them before, and then you only have to render on that shadow map the dynamic objects. Okay, it's a trick I would love to code one day. I didn't have time to do this kind of trick before, but I think it's an interesting approach. Another classical thing is skip small objects, because small objects won't have much effect on the shadow depending on the textile size of the shadow map. So yes, if the small object bounding box is smaller than some threshold, you just don't render the shadow maps. You don't render in the shadow map, because remember that even if an object is small or big, the time it takes to render is always like complex. So don't think that because it's small, it's going to render faster. Doesn't have to be that way always. Some engines can use simplified versions of the message for the shadow map, although this is not simple to use, because if there's discrepancies between the mesh that you see and the mesh that generates the shadow map, you can get strange artifacts in some situations. And also, obviously, when you render, the faster is the shader, the better. So the shader to generate the shadow maps has to be super simple. Like, we don't care about the color, so it has to be only render flat color all the time, and that's it. Okay? Okay. So this is to speed up the shadow map as much as possible. And from here on, we assume that you have generated shadow map from the point of view of the light, and you have stored it in some texture. We will see how to do that, and then we are going to pass that texture to the shader and the light pass. About point lights, as I said before, the problem with a point light is that you cannot put a camera in the position of the light, because, well, point lights see all directions, and GPUs don't support to render spherically. We have cube maps that are these 6 faces, but you cannot render instantly to the 6 faces of the cube map, although there's some hacks to do that, but I would recommend you explore that. So the best approach to render for a point light is you render 6 times the whole scene. So 1 in front, 1 to the back, 1 to the right, 1 to the left, 1 to the top, and 1 to the bottom. 6 times the whole scene. You store 6 shadow maps, and then from these 6 shadow maps, then you can try to use it during the render. It's super expensive, as you can see, to render 6 times. So there are tricks. Some engines have a solution where they only render the scene twice, although it has some artifacts that I won't recommend you, and it's a lot of math that I recommend. They render one to the top and one to the bottom, for instance. Or another approach could be that you render only once the scene, but you use a special shader called geometry shaders that to split the render to different 6 views. Okay. Still, all of them are super advanced. So the first step always, if you want to have point lights, is shadow maps for point lights, is that you use the approach of rendering 6 times. Okay. Another problem, obviously, as I said, is we're going to have resolution problems if the shadow map is not big enough, or if we stretch the shadow map to cover more area, because you don't want to have areas where the shadow map is not here. Here's an example of the shadow map only covers a small area of the map, and everything that's outside, because we don't have information about how far it is, we cannot compute the shadows. So in this case, we are saying if it's outside, you just render without shadow map. And you can see how these poles here, they don't have a shadow, or how this shadow here gets cut here. So then obviously the first idea is to make the shadow area bigger, but the bigger you do the shadow area, the bigger the artifacts are going to be. So no solution for this problem. You can see this problem happens everywhere. This is Fortnite, and you can see how the shadows of the boat appear as the camera moves, because, well, as I said, this is a common problem. The shadow maps has a limited area, and you want to have solutions for when it has to cover more area. Another problem you're going to face, and it happens a lot, is that when you store the distance for every pixel to the light on the shadow map, those values are going to be truncated to the precision of the shadow map, to the precision of the texture. In this case, usually it's 24 bits. And that's a problem, because you're going to have like some adjustments, like the depth you're storing is not exactly the depth. It's like some rounding of that depth. So when you're rendering the object, you compute the depth from this point to the light, and then you compare it with the depth stored in the shadow map, even if this point should have exactly the same depth, could happen that it's not exactly, there's a small difference. And because we are comparing it, we're saying, or it's bigger or smaller, what is going to happen is we're going to have these strange patterns artifacts. They have a name, we call them usually shadow acne. It happens because we have problems of precision. So there's a trick to do this. The most common trick is don't compare the both values directly. You add a tiny threshold, so it doesn't have to be exactly like if A is smaller than B. Could be if A plus 0.001, it's smaller than B, and then you will mitigate a little bit the rounding. But that introduces another problem that we will see later. Because as another problem that's good to understand, and this may sound strange for you, is that the depth buffer are not stored linearly. Okay, it will take me half an hour to explain all this, but let's think in that sometimes when you store data on any variable, we usually work in linear, so we use, I don't know, the same amount of bits for the difference between 0.1 to 0.2 that the difference between 0.9 to 1. Okay, but that doesn't have to happen in some situations where the values, they know that you want more precision in some like smaller values than in other ones, and the depth is not linear. Because it's not linear, you're going to face different problems. Farther objects will have more problems with shadows than closer objects. Closer objects to the camera will have more precise shadows than farther objects from the camera. There's a lot of people who have tricks to how to linearize the set buffer, so you don't have this kind of different approach of precision, because there's a lot of precision stored in the first meters of the first units, and very few precision in the farther ones. Okay. As it would be nice when you have a big C like this one, that amount of information stored in the shadow map for farther away pixels is very few in comparison to the amount of information stored for the closer ones. So because I don't care that there's a shadow map between, I don't know, 1 millimeter here and the next one, but I care here that 1 millimeter away it has a better shadow map. So it would be nice to have a solution that scale, the farther it is from the camera, the less resolution has to have the shadow map. The problem is that this is not solvable directly. You cannot have a projection matrix that the farther it is, it adjusts, because, well, there's some limitations on GPUs. So we have to find a workaround to this problem. Also remember that I say for every light that we're going to render, we need to pass the shadow map if that light has a shadow map. And shadow maps are textures, and GPUs have a limit of the number of textures they can use. You cannot store, I don't know, 6,000 textures on a shader. It doesn't work that way. But if we have a lot of lights with shadows, we may need that. So we need a problem to pass the limit of shadow maps that we can use. So now let's go to the implementation of all this. We know all the problems, we know the tricks. Let's see how we can achieve a nice shadow map on our engine, okay? Although next class I will do the implementation on this step by step. I'm going to give a brief explanation now, and in the next class I'm going to explain it in detail. So, well, this is if you want to linearize the set buffer. We are going to need to linearize the set buffer if you want to do a preview on the screen. Because if you don't do the linearization of the set buffer, if you try to visualize the set buffer, you will see how you don't see much on the screen. You will see everything is white, and this is a common problem. So we need a way to be able to transform the depth buffer into a linear value, so you have this beautiful gradient from far to close to the camera of the objects. And here's an example. You have a depth buffer generated by the GPU, and in any moment you want to read it, visualize it on the screen, and you want it to be linear because linear makes more sense for eyes. Then you have to do this operation to every pixel. You can make a shader, you pass the depth buffer, you pass the near plane and the far plane of the camera, and then you do this operation on the shadow map, and then you get this linear Z that you put it as a color. You will see the beautiful gradient that you have seen in many of the slides. Okay, so how we render inside the shadow map? We're going to use FBO. What's an FBO? FBO are these classes that have these, you define an FBO. The thing is that we don't want to store color, we only need the depth. If that's the case, you can say set depth only, and you specify the size, the width and the height, and it's going to create a texture that has this square shape, and it's not going to store any information about the color buffer, so you can skip all that, okay? Then as soon as we bind to this texture, keep in mind that we only need to create the texture once. Don't create it every frame, because if you create every frame, you're going to crash the system because you're going to get out of memory very soon. So we create it only the first time, and then we bind it. When you bind to the FBO, means that from now on, everything you render is going to be inside the shadow map. Okay, then you can see here I'm putting color max false, 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 false. This means you're telling here to the GPU, hey, I don't care about the colors. You don't need to render the colors. When you set up the color max to false in all the channels, red, green, blue, and alpha, the GPU can do some optimizations because it knows that the colors are not necessary. So you can skip the parts where it accesses the color to store it. Then we are going to clear the depth buffer, obviously, because we need to store the depth buffer, and because you are going to reuse the same buffer again and again, so we clear it because we want to be super far away. Then here we should be rendering everything that's on the scene. And when we render everything that's on the scene, we better be sure that we're using a shader that is super simple. Like we only need to render the depth of this object. So the color buffer can be anything like from white, and that's it. Okay. Finally, when we have rendered the whole scene, we stop rendering inside this texture with the unbind. That means like, okay, we have finished it. Okay. And now, from now on, we set up everything the color max again to true. Otherwise, we won't be able to see anything on the screen when we render in the future. Okay. So this should be the main loop to generate the shadow maps. But to generate the shadow maps, we need to first position the camera. We're going to start with the directional light because the directional light is the simplest one. So we create a camera. We can have this camera like a global and reuse it because it's not like we're going to do many things with this camera besides using it now for rendering. So I'm going to set up the camera in the position where the camera should be following the light. So the light position and the target where the light is pointing at. And as an app, it's 0, 1, 0 usually. We have to set up if it's a spotlight, it's a perspective. If it's a direct light, it's an orthographic. Okay. In the case of the perspective, remember that we need to set up the cone angle, the aspect, the near, and the far. You can see here that we are using the cone angle as the fob, because obviously if your camera is a spotlight, so if your light is a spotlight, the camera has to match the cone perfectly. So cone angle, which one? Because remember we have two cone angles, the minimum distance and maximum angle. So minimum angle and maximum angle. It has to be the maximum angle, obviously, because it's the one that covers the whole light. The aspect ratio that we computed. I mean, it's going to always to be 1 because our line maps are always going to be square. And then a near and a far values, okay? And on the case of orthographic, we have to specify how much area we want to cover of the 3D space because, well, suppose that directional lights should cover the whole map. In this case, we are going to have this light area, okay? Every light have a property that says how big we want it to be. And then when you set an orthographic camera, you have to set the distance to the left, to the right, to the top, to the bottom, to the front, and to the back. So in this case, because the area is the total size, then we divide it by 2, and this is half size. So we use for the left minus half area, to the right half area, to the top half area multiplied by aspect, to the bottom half area minus half area multiplied by aspect, for near 0.1, and for far light max distance, okay? So with this code, it works for spotlights and for directional lights. We will have a camera that's going to render at least the main area visible by those lights, okay? Then, as I said, the shader, the color shader has to be the fragment shader, should be something as simple as this. I mean, we don't care about the colors on the inside the shadow map, unless we were using that trick I said before, where we are storing the colors, or are using the color to store the distances, okay? Which I think is an interesting approach. You get better quality shadow maps, by the way, but for now we don't care. Okay, so we're going to need two things when we are going to use this shadow map during the illumination pass. First, we're going to need the depth texture, so you can get it from the VO, like in here. So you have this shadow map. Here's the depth texture, but we are going to call it the shadow map because it's a texture that stores information of the shadows. And then we are going to pass this to the shader in the future when we want to render something with shadows. And also it's important, we need to store the view projection matrix. You store it on the shadow projection, this variable here that we are going to also pass to the shader in the future to say, hey, this is the view projection that you need to use to project any wall space to the shadow space, okay? Because we want to avoid having shadow acne, as I said before. By the way, I don't know if I show you the shadow acne, but so you can see it. If I don't apply shadow, the bias, you get this, and you can see these strange artifacts. And as soon as you push a little bit the shadow map, just a little bit, you can see how it disappears, okay? I'm adding just, when you compare both distances, I'm adding a little bit distance. If you add too much distance, by the way, you're going to start seeing this ugly artifact where things are going to lose the shadow. So you can see here how this part of, I'm pushing so much the shadow that this is starting to be too far away, okay? So that's why you always want to keep a value small, but not so small that you have artifacts, okay? Remember why this happens. So I didn't explain very well, but it's important that you understand. So if I have this shape, I put the camera here to render the depth buffer. So the camera is going to store the depth buffer of this on these pixels. It's going to be, and the other pixel is going to be here, and outside of the sphere is going to be here, okay? From the point of view of the light, which is here. Okay, so when I'm rendering this pixel in the future, I'm going to ask, hey, what's the depth of this pixel? And it's going to tell me the depth of this pixel related to the camera, the distance, and then I'm going to compare it to the one on the shadow map to know if it's in the shadow or not, okay? The problem is, because I said there's some precision problems, it could say, no, this value, the depth, is a little bit in front of you. So you can, oh, this is in front of me, then it means there's something in front of me, then I don't compute the shadow map. And then I say, this is black. So when the illumination passes, I say this pixel is black. There's a trick to solve this problem. I will see it in another slide in the future, which is, instead of rendering the front size, okay, because the front side, the side that is facing the light, is the side that is closer to the light, but also is the side where the shadows are going to be. The shadows, where the illumination is going to be computed. There's another trick to say, no. On the shadow map, you compute the back face. So you're going to render the back face of the objects, not the front face of the objects when you compute the shadow map. So when I compute the shadow map here, it's going to say, no, the shadow starts here, very far away. So, okay, there's no problem here. So that artifact I was talking before doesn't happen. And here, when you do compute here, it's going to see that there's already something in the front, so it disappears. in designing here, I can control that factor. So I'm going to put the bias to 0. So I have all these artifacts. But I'm going to control and say that instead of rendering the front face, render the back face of the objects when you compute the shadow map. And you can see how the problem disappears without any kind of, so now it's nicer because you can see how the shadow touches the object. If I didn't enable this and I use the bias, if the bias is a little bit big, you see how the shadows start not touching the places where it should be touching. And so nice, but there's another problem here, that because this shadow starts very here, when objects that are very close to the point where the shadow starts, you get these ugly artifacts. So this trick doesn't work also in all the situations. When you want self shadows, doesn't work very well. So anyway, there's no perfect solution. So sometimes you want to leave the artist the possibility to play around with these properties by themselves. Okay. So as I said, we want to solve the bias problem. So the best way to solve the bias problem is that we pass to the shader this bias, and we allow the artist to control it in the editor, and that's it. Okay. The bias, by the way, we're passing a number. You can see it's very small. It was 0001 because we only want to push a little bit, because the set buffers are in non-linear space. If you use this value directly when you compare, sorry, before the conversion and everything, no, sorry, after the conversion, you're going to have problems because this size is going to be, this value is going to be different if it's close to the camera, to the far to the camera. So anyway, in our code, we apply it in a moment when we know we are in linear space, not when we are still on this kind of strange space of the depth. So the shader at the end, the shader looks like this. You can see that it's not so complicated. Let's go one step by one step. We have a wall position here. We're going to multiply it by the shadow view projection to convert it to the view space of the light. Okay, we're going to call this pose. But when you multiply any position by the view projection matrix, you are in homogeneous space. You don't know what's homogeneous space, don't worry. It's also hard for me to understand sometimes. It's just how matrices work on projection matrices. By the way, this only applies to projection matrices. For regular orthographic matrices, there's no homogeneous space as far as I know. So to convert from homogeneous space to clip space, you have to divide by the result W, okay? Just you have to trust me in this because that's the way it is, but that's it. So now we have this point on clip space from -1 to 1, but we wanted to have it on UV space, which is from 0 to 1. So in this case, multiply by 0.5 and add 0.5. So now this coordinate here, shadow UV, tells you in the shadow map in which pixel exactly this wall position will fall. Could be outside if this point was outside of the point of view of the light. And let's assume that it's inside now. So now we need to compute the depth of this pixel to the light. Okay, so this view pose on the XY, we use the XY to compute the UVs, but we also want to use the Z to divide it by W to get this depth from -1 to 1. Sorry. Okay, and to do that, what we have to do is divide it by the W. This is the real depth, the distance from the point to the light, the true depth, all the distance that it is, and we convert it from -1 to 1 to 0 to 1. Okay, and now we go take the shadow UV, go to the shadow map, and we read the distance. You can see we only read the X because we don't care about when you read the texture like shadow map, all the layers are 0 plus, besides the red channel, which contains the value. So now we have a shadow depth here and a real depth. We have two depths. One is the one based on what the shadow map says, and one is the distance from this point to the light. So we compare them. And if one is smaller than the other, it means it's a shadow, otherwise there is no shadow. So here I use this shadow factor, and then I'm going to multiply this on the pixel. So as you can see, some steps could be a little bit complicated at the beginning, but you just put them together in the shader, and you have a way to compute if it's closer or not. And as I said before, this pixel could lay outside of the shadow map. If that's the case, well, depending, if it's outside, you can see here, if the UV is minor than 0 or the UV is bigger than X, the same for X and for Y. That means that the pixel is outside. You can do whatever you want to. In this case, if it's a directional light, then I put maximum light, so the shadow factor is 1. So then when I multiply by the color, is going to stay the same. And also what happens if it's behind or in front of the shadow map. We can check the real depth if it's behind or if it's in front of it. Okay. In this case, well, here I'm putting always to 1. In the case of the cone, if we are rendering spotlights, it will make more sense to put 0. And what happens if I want to send several textures? Because it can happen that sometimes you want not to send one single texture, but several. In this case, for the forward rendering we are doing, it makes sense that if we are going to pass like 4 lights at the same time to the shader, we have to also, maybe we have to pass 4 shadow maps. So if that's the case, the engine supports to pass several textures, so you can define an array of textures on the shader, and then you can pass everyone separate like this. But remember always that you need to specify the slot for every one of them, so you don't have infinite slots, okay? And that's mostly it. With that, you will have shadows. You will see it on the next class. Tricks that you may want to use. The thing about having different textures for every shadow map could be a little bit complicated to code because you need a lot of different objects, so different textures on the shader. So one trick I usually use, which is very simple to code, and I recommend you to code it, I give you points if you code it on the assignment, is that you have one single texture, and that texture contains all the shadow maps of your scene, like you can see here. Okay, this is called a shadow atlas, and I say it's very cheap because the only thing you have to do is, instead of creating a lot of shadow maps, you create one shadow map, which is very big because you're going to have to fit all the shadow maps inside. And when you're going to render the shadow map, you limit the render to one specific area. Remember that to limit the rendering to one specific area, you can use this GL viewport and you specify the area. Okay, in this case, it has to be in pixels. So you can say, I don't know, if this is 124, then I don't know, 256 by 256. When you specify the area, you specify the pixel where it starts and the width and the height. Okay, so you have this area where you want to specify the shadow, and then you just do the render as I said before. Okay, super simple. This here, the GL scissors. GL scissors is to force the GPU to not be able to render outside of the area. By default, if you have a viewport set to this area and you render, you're never going to render outside of that area. There's only one case, is that if you do the clear buffer, like here, the problem with the clear buffer is it affects the whole buffer. So even if you have set the viewport to this small area, if you do the clear, it's going to clear everything. So all the shadow maps you have created before is going to destroy it. So the best way to avoid this problem is that you set the GL scissors, because scissors blocks the GL clear to clear outside of this area. Okay, so you enable the scissor test, and after you have rendered everything, you disable the scissor. Oh, you can disable it also if you want after the clear. Okay, so you have a way to clear only one part of the shadow map. Then you render everything, and then finally, when you're going to read the shadow map from the illumination pass, besides sending the shadow map and the shadow projection, the view projection matrix, you also send the area where you rendered the shadow map. And then the UVs, you will have to adapt them. If the UVs I showed you before, which go from here when you're reading the texture, shadow UVs, these go from -1 to 1. Now you have to adapt it so they go from 0 to 0.5, for instance. Okay, super easy to do, and it makes everything simpler. Having one single shadow map makes all the code much simpler because you don't have to be passing a lot of shadow texture constantly. Here are more information about optimizations, how to detect if lights are outside or inside the view, stuff like that. The bias, how to solve the bias problem. There's another problem here. Maybe tomorrow, if I have some time, I can show it, which is that I didn't say anything, but usually when you have a light direction, so if this is my map and I have here a house and I'm here, I have a light that is the directional light for the sun, which is here, and I'm going to render a light map of this area. The problem is that if I walk in my map and I go here, and here are more houses, it doesn't make sense that the light, the sun stays in this position rather than this area, because this area is outside of where I am. I want to see shadows of this area, not this area here. So there's usually a trick that many engines do, which is we move this light, okay? So instead of storing this light as a position in wall space, we store more like a vector. Now, this is the important thing of this light. And every time I have to compute, I put it where I am, like I go in the opposite direction. So this goes here, then I go in the opposite direction, some distance, I don't know how much, and I put the light here, okay? So every time I move around, the light map of the directional light is going to follow me, because the sun is supposed to be always in my area around, okay? And that's nice. You can walk and you will see how the shadows appear around you all the time, no matter how big the map is, and you don't have to have a very huge area of the light map for the directional light. But if you do that, you're going to face this problem, which is that when you move, the light map is going to have tiny changes. And because the light map is going to have tiny changes, you will hear how the shadow maps start blinking a little bit, because they are generated every time with some offset, and that offset can make that the shadow map is not exactly the same as the previous one. So you have this strange offset. There is a hack for that, which is before you use the view projection to render the whole scene, what you're going to do is try to clamp or snap the view projection matrix to some grid. And for that grid, we're going to use the size of the textiles in wall space. Using this trick, you can have, well, when you move, the camera is moving, but it's moving like fixed amounts, and those fixed amount matches the size of the textiles, so you won't see this flickering. Anyway, if you want to play with this, feel free. Other problem: what happens when we have a huge scene like here, and we want to have shadow maps in all of them? I mean, as I say, directional light, you can move it around the camera, but it's not going to work always. So the most common solution that all the games do is have cascaded shadow maps. The idea is I don't have one shadow map, I have 4 for the directional light, which the directional light is the most problematic one because it has to cover more area. So we're going to render a shadow map of the area around the camera, and then another shadow map of an area bigger, and another shadow map for an area a little bit more bigger, and another for the whole map, okay? On this one, because it's closer to me, all of these, by the way, they will have the same resolution. So this one over here is going to have a smaller area of the wall, but with more resolution, which is nice because it's closer to the camera, to me, so I can see better shadows here. And then the second one is going to have covers more area, so the resolution being the same on the texture means that they are going to have less detail, the shadows, and so on and so on. Okay, 4 cascades is the common approach usually used by most games. To code this, super simple. Instead of one shadow map for the directional light, we have 4, and then we have to render 4 times the shadow map of the directional light. Obviously, 4 times it has a lot of cost, but it has there's something good about this, is that this one and this one, we don't have to update it very often. These are for very far away objects, so we don't care so much. So we only update this one maybe and this one every frame, and this can update this every frame and this every 2 frames. And these ones over here, we only update it like, I don't know, every 5 or 10 frames. So using that trick, you can have very long shadows on your map, okay? Also, some engines, by the way, these ones, they compute them for the whole map on a startup, and they never change it because they already have the shadow map for the whole map, and they know that the map is not going to change so much. The only problem when you have cascaded shadow maps is this problem that you see here. In this case, that there is this discontinuity between when one shadow map finishes and then a cascade starts, and it's very visible in many games. So there's always tricks to try to blend when you change from one cascade to the next, do some sort of blending, like the shadow maps extend a little bit, and then you have to do some linear. It's not easy to code this. Well, I mean, you have to pass more information, but if you want to play around with this, it's doable. Here, there's always people saying that using the non-linear depth information on the shadow map is usually problematic. And when you have open maps, so the best solution is to linearize the depth when you compute it. sorry, the shadow map. So here, as a trick that people use to do that, here's a link about how to do that. As I said, this only apply when you have very big maps, and using the buffer non-linear can make that things closer to the camera have better shadows than things that are far away from the camera. Another problem is the light bleeding. Usually the place where the shadow, like if you have these contact objects to this floor, this is very thin, and because it's very thin, the shadow starts so close that you have the problem that the shadow is passing a little bit. The light is passing because the bias that we added. Obviously, if the object is very thick and you're starting with this face here, then this distance is big enough so the shadow map doesn't appear. So the bleeding doesn't happen. I said before that there's a trick of rendering the inside faces, not the outside faces, if you want to. This solves some of these problems in some maps, not in all of them. There is also another approach where you render not the front face, not the back face, but the middle face, which you have to compute first, which is kind of painful to do that, so I don't recommend it, but that solves this problem in many cases. Other thing is that we pre-compute the shadows at the very beginning of the application and don't touch them again if nothing is moving. And if something is moving, the shadows won't match. That's it. Like in this case, you can see this character, the shadows on the scene, but he doesn't have shadows because I say that this object, because it's walking, I don't want to generate the shadows. So for point lights, as said, 6 renders, super annoying, but you can do it if you want to. Here are some tricks about how you can compare the depth when you're using 6 images. I usually, in my engines, every time I have to do point lights, what I do is I create a shadow map that it's vertical, has all the 6 faces. And here is a code that if you have the 6 faces vertical, you can convert from any direction of the wall space to the UV that matches these 6 faces, okay? By the way, you can render shadow maps to cube maps if you want to. The GPUs support the possibility to render inside a cube map. You have to render first one face of the cube map, the next one, and then you can pass that cube map to the shader like a regular cube map. That's very handy, although I have to tell you that accessing the depth in these cases can be a little bit painful. And there is this super trick I never tried, I read it not long ago, where you can use a geometry shader where you dispatch every triangle that you render to every face of the cube map. If you do this, that means that you can have a kind of simple way of one render call render the whole cube map for the point shadows. Another problem is that you're going to face a lot is that the shadows will be very sharp. You will see this. There are tricks to make the shadows a little bit better. Here I say there's this function called chamfer to the shadow. This function is an implementation of some of the OpenGL versions. I don't know if it's still available, but this function allows you to do this. It does some fetches a lot of samples around a point and then tries to do the average and solve this problem. So you get a little bit more softer shadows. Otherwise, you have to do it manually, which means you have to compute a lot of, for every point, instead of fetching one time the texture of the shadow map, you fetch 7 around a radius, and then you do the average, and then you get a softer shadows, okay? So this is called PCF. So no PCF with PCF, and if you PCF, you also use bilinear filtering, you get these nice soft shadows, okay? But at the cost of more accesses to the shadow map, which is not so much expensive. There's another trick if you want to render for spherical lights using the paraboloid. Don't recommend, produce a lot of artifacts if you don't do it properly. And also most of the engines, when they have to have shadows, they use this approach to make the shadows. It's called variant shadow maps. The idea is that after you have generated the shadow map, you have to apply some process on top of the shadow map, like an extra shader that blurs that shadow map and computes some minimums and maximums. And then when you render the shadow map and the illumination path, you read from the values, you have this average of the depth. And using that average of the depth, you can compute these kind of nice soft shadows. Although you can see here, it can produce some artifacts sometimes. And the final trick I've seen is that the problem when you push the bias is that you will lose the contact point, okay? This is usually called Peter panning because objects look like they are floating. So if you reduce the bias, then you have the problem of the shadow acne. So some engines, what they do is that they compute the shadow maps and they use the shadow maps with a bias, but this area here, they compute the shadows using another technique called contact shadows, which is using the depth buffer of the camera, the real depth buffer of the frame that we are rendering, to know if there's something closer in this direction. We will talk about this in a couple of weeks. For now, just so you know that there's tricks to solve the Peter Panning of the bias using another pass on the render pipeline. And finally, obviously, if you have these powerful ray tracing cards, all the problems of shadows are gone, because from the shader you can send a signal, a message to the GPU and say, hey, is there an object from here to the light? And it will tell you yes or no. And because with that you can make beautiful shadows, translucent shadows. You can see here how the shadows are semi-translucent, something that we cannot accomplish with the regular shadow maps because they only store one distance. And more cool tricks, also shadows for point light super easily. There is one trick that the Unreal uses for having ray traced shadows without using ray tracing, which is they store an SDF of the whole map. An SDF, we will talk more about SDFs in the future, but just think it as a way to store in a texture all the information about the shape of the wall, okay? Where are everything inside this texture? And there is a solution that allows you to traverse this structure of data very efficiently. So you can move super fast inside this structure if you want to know if there is something colliding in one direction. So first you have to generate this texture. This SDF is more like a volumetric texture that stores where are objects and where are not objects. And with the addition that if you want to move in some direction, the texture can tell you how far have you moved, should you move if you don't want to collide with anything, or until you collide with something. Because of that, you can throw rays from the shader. You can throw rays in directions to know if there is something in the middle of the light or not. But as I say, this is very complex and it's interesting to know about it, but we are not going to use it. That's it, okay? So here there's a slide from the one of the talks from 2016 for the game Doom Eternal, or Doom Eternal, no, the Doom, the previous Doom. And here you can see we read this slide about how they managed to do the shadows. You can see that you can understand some of the topics, like here they say they catch the shadows in an atlas, that the atlas is 8K by 8K, 32 bits per every pixel, variable resolution based on distance, so the shadow maps can change depending on how far you are from the camera. Optimize the mesh for static geometry, so they use special meshes for the shadow maps. If the light doesn't move, catch the static geometry in the shadow map. So stuff like this. So at the end, my idea is that when you see these slides, at least some of the topics you understand what they are talking about. Okay, I recommend you have some time that you check these slides. They are very interesting and they want to explain all the tricks inside. And finally, there is a video I recommend you to watch. Is this video from Unity where they were talking about the render pipeline, and in this video you see the super beautiful shadows and all the tricks that they use. Okay, and I guess that's it for today. A lot of references I recommend you to check if you have some time. Always, these references are always interesting. They talk about these topics in depth by professionals, so it's always interesting to know about them. And on the next class, my idea is to explain all this. I'm going to code all these topics in the engine. You will see they are much simpler than they look like. Okay, so that's it for today. Sorry, I couldn't make the class personally. I would love to be there, but I couldn't. So if you have any doubts, use the Discord or send me any email and I will be happy to answer. Okay, see you in the next class.